also for the nice organization of the seminar, and thanks for the warm welcoming that
Sa che devi uscire dalla presentazione.
Okay. Okay, let's start again. So I was saying that I received a really warm welcome, and it's a great pleasure for me to be here. It's my first time here at the Institute, and so, well, it's nice to see you in person. So today I would like to talk about our last years of research regarding AGB stars, and in particular about the dust production from these stars. This was done mainly at the Observatorio of Rome, but also many people were included and involved and collaborate to this. Let me introduce among them the youngest. There are Silvia Tosi, who is currently doing her PhD in Rome under the supervision of Paolo Ventura, Devika Kamath, who is in Australia, and me. And also Esther Marini, who recently finished her PhD, always in Rome, under the supervision of Paolo and me. So let's start immediately with a question. Why do we really care about AGB stars, not only on the from the stellar evolution point of view? And let's spoiler immediately the reply, because well, these are stars that during this phase lose a great amount of material under the form of gas, which was reprocessed during the AGB phase and in previous phases by the internal nucleosynthesis. So then it goes to enrich the interstellar medium. And also they are major sources, stellar sources of dust for galaxies together with supernovae. So all this material then goes in the life cycle of galaxies and the universe to form, of course, enrich the environment and form other objects. So now, with my talk, I hope to convince you about it. So let's start from really the beginning. Who are AGB stars? What is the AGB phase? It's the asymptotic giant branch phase, which regards almost the final life of the low intermediate mass stars. We are talking about stars with mass between 1 and 8 solar masses that after the exhaustion of the helium in the core then rise up to the asymptotic giant branch, evolving at brighter and brighter, higher and higher luminosities, and that can be up to even 10 to the 4 or 10 to the 5 solar luminosities. So they are really bright objects. And of course, they evolving through this asymptotic giant branch, they also cool down, becoming even more giant and expanded, and they can reach a really cool temperature, even up to 2000 Kelvin. The structure of these stars is made of, and if we look in terms of mass, an example is here. We have a degenerate core made of carbon and oxygen. Then we have above the core the two burning shells which sustain the stars. Which sustain the stars. Well, the helium shell is activated during a phenomena that is called a thermal pulse, but then most of the time the energy for the stars comes from the helium hydrogen burning shell via the CNO cycle. And then we have an expanded envelope, which is also quite massive, and you see here in terms of radii that is really tenuous and expanded and weakly bound to the internal region of the star. This is one of the reasons why these stars during this phase lose entirely this envelope with their mass loss rates that are up to even 10 to the -4 solar masses per year. But this envelope during the AGB phase undergoes to some mixes and reprocesses. So this is material really enriched on the chemical side. And what else after this? Well, here we have a scheme of the circumstellar envelope. So the envelope is also characterized by pulsation shocks that levitate, let the gas levitate and arrive and cool down, forming a cool and dense wind, which arrived in the region where temperature and densities are favorable to form dust. And then if certain amount of dust is formed, then this dust can be ejected and pushed by the stellar radiation towards the interstellar medium. This process is what we want to understand better, and via this process we want to quantify the amount of dust, the mineralogy, and the grain size distribution that these stars can produce. And to do this in 2006, already other groups started to develop a simple scheme to describe this wind dynamics and the dust production, which rely on a quite simple scheme, but which is robust. And here you see some of the equation that describe the wind dynamics, where we have that the ratio between the radiation pressure from the star to the dust grain compete with the gravitational attraction from the central object. And once we have that, the extinction produced by the presence of a large amount of dust, which create an opaque matter, we have that the radiation pressure from the central object dominate, and then we can have the acceleration of the wind. But this key quantity is mainly determined by, firstly, the amount of dust that we can form, but of course also from the type of dust that we form. So let's see. One would, in principle, think that, okay, we are talking of oxygen-rich stars. Oxygen is one of the basic components that is needed to form dust. Otherwise, we could have carbon dust species. But well, okay, we are in an oxygen-rich environment because oxygen is more abundant than carbon. And also we really care about which of the two elements is more abundant respect to the other, because in the circumstellar envelope there is the CO molecule, which is extremely stable, that bound all these elements, and what is left for the dust condensation is only the element in excess between the two. But actually, we are not always in oxygen-rich environment, because low mass stars with masses below 4 solar masses during the AGB phase experience the third rejap, which is a mixing that arrived where in the internal region of the star, where there are the ashes of the 3-alpha reaction. So it's region that are enriched in carbon, and this carbon is dredged up to the surface, and several episodes repeated after each thermal pulse during the AGB phase can lead the star to reach the carbon star stage in this range of masses, more or less. And then so if we have a carbon-rich circumstellar envelope, then we will form mainly solid carbon and silicon carbide. While this is not always true, in particular because for the more massive stars. Above more or less 4 solar masses, we have a phenomenon that is called the hot bottom burning, because these massive stars, massive AGB stars, reach a high temperature at the base of the convective envelope, higher than 30-40 million Kelvin, that activate a proton capture nucleosynthesis that burn the carbon that would have been mixed eventually in the envelope. So the hot bottom burning prevents the occurrence of the carbon stage for during the life of the AGB stars in the more massive stars. So in this case, we have oxygen-rich environment, and in this circumstellar envelope, we form mainly silicates and alumina dust. Okay, so we had at that time, it is almost 10 years ago, we had a scheme, we had evolutionary models that clearly describe the AGB phase. And so we could apply and couple this scheme for the dust production to the stellar evolution code that is being developed several years ago by Italo Mazzitelli and Paolo Ventura in Roma. It is the atom code. And well, it is really important to couple the two things, because of course we really need a clear and detailed description of the of all the alteration that we can have in the surface chemical composition. Also, we really need to explore the entire AGB phase, because temperature, mass loss, luminosity of the stars evolves and changes, so it of course affects the dust production. So to have a complete view, we couple this approach and produce a wide grid of models, which are summarized here in this plot that show the total amount of dust produced during the entire AGB phase for different initial masses between 1 and 8 at several metallicities. From this plot, we can immediately see this dichotomy between low mass and high mass among the AGB interval of masses. We see here that this range of masses produce mainly solid carbon. And this is, as we said, because of the third reject that enriched their surface. And these are, as you see, this dust production doesn't clearly depend on the metallicity of the star. There is not a clear trend. And the reason is that what really matters is, of course, the how much dense is the gas, so the mass loss process, but also the key element is necessary. So the carbon that is available is what really lead the dust production. And carbon is a primary element that is a result of the 3-alpha reaction. So there is not a direct link with the metallicity in this dust production. While in the more massive regime, we see the effect of the hot bottom burning, because we expect to form mainly silicates and also alumina dust. And we see a clear trend with the metallicity, because the key element in this case is silicon, or rather the aluminum. And of course, this depends on the initial chemistry considered. We also have a trend with the initial mass of the star. This is more connected to the mass loss rate that are expected for these stars. More massive it is, more denser wind we expect, and larger envelope are lost, so we can produce more dust. Anyway, let's just highlight also the evolutionary timescales that we can learn from this exploration. So we expect that in really quick time to produce silicate dust from AGB stars because the evolving times are some hundreds million years or even much less. While for the greatest production of carbon dust is expected for around 2-3 solar masses, depending on the metallicity. But well, so we are talking about some giga year, or less. And okay, so with all this prediction, what we wanted to do is to see whether we can reproduce the observation with this approach, and to make this comparison, we had to explore how change the spectral energy distribution because of the presence of dust, because dust absorbed the radiation and then remit, and the emission is then at longer wavelength. So and it depends, of course, on the type of dust that is present in the circumstellar envelope. So these are the representative evolution of the spectral energy distribution for a typical carbon-rich star, starting from the beginning of the AGB, when we do not expect the presence of significant presence of dust. And then you see the evolution, the peak of the SED moves towards longer wavelength. The emission is dominates in the infrared. And we can see some feature, for example, for the silicon carbide, but the main emission is in the continuum due to the solid carbon. And at the end of the AGB phase, when a lot of carbon has been dredged up by the star to the surface, we reach the highest obscuration. The star is completely enshrouded. As you see, is invisible in the optical and eventually even in the J or H band. On the other hand, oxygen-rich stars are characterized by silicates which are less opaque, let's say, to the radiation, so they do not obscure completely the star, but they really characterize their SED because they have two features that are at 9.7 and 18 micron. And well, here the evolution really depends on how you model the mass loss, which mass loss prescription you use. But anyway, I don't enter in this detail now. So, well, having all this description mapping the AGB evolution with the synthetic spectra, we had the possibility to compare with whatever survey in the infrared we would like. We started with the Magellanic Clouds. They were our test laboratory to see whether we can reproduce the distribution of the stars, the AGB population, in the color and color magnitude diagrams in the Spitzer band, mainly because Spitzer really well mapped those galaxies. But then once we have tested, we realized that we could really characterize their population in terms of the initial progenitors of the star, the metallicity, and also trying to estimate the dust production rate expected from these stars. Then we explored other dwarf galaxies where we could have the data available. I make you an example, which is IC10. You see here, assuming an initial mass function using our evolutionary tracks of the AGB evolution plus the dust production in the circumstellar envelope, and knowing a star formation history already determined by others, we were able to construct a synthetic population to be compared with the AGB population, with the AGB data observed in this galaxy. Here, there were available only the 3.6, 4.5 micron bands of Spitzer, so we relied also on the 2 mass bands to make this analysis. What is interesting is that we can characterize the stars that distribute along the color magnitude diagram. You see, we have a branch. Let me see if I find again that. Okay. Here there are the carbon stars that are evolving towards the reddest part of the diagram along this branch. This is a really clear feature that can be seen in many galaxies that we have analyzed, because yes, this is the fact that I was telling before. The solid carbon has an extinction coefficient, it says optical properties that really obscure the star. So this difference among the two types of dust that characterize two different range of masses allows the determination of two paths that are traced by different masses. So you have that stars within, let's say, 1.5, 3 solar masses will evolve along this branch at increasing obscuration and redder colors towards the end of the AGB phase, while more massive AGB stars evolve more vertically, because of the presence of silicates, which alter the spectral energy distribution in a different way, and also, of course, they are brighter. So this also is a matter of fact. Well, also making something more quantitative, we could also explore the limits, the upper and lower limits of the star formation history that we used, giving our best guess for the star formation history, and these are the epochs that were. We expect that these stars were formed. So we can reconstruct also the formation epoch. And well, last but not least, the dust production rate. That is an estimate. Of course, it depends on how much data you have available to explore several galaxies. But in this case, we were using a complete sample, so we could explore this measurement. And well, now there is the JWST era. So all these studies would be done even better and extended to larger edge and boundaries and horizon thanks to the JWST. And here you see this is the LMC, and if we move the LMC towards further distances, these are the limits that we expect as the deepest point of the CMD diagram where that we can reach. You see that the AGB phase is really bright. So really it is unique to trace even further distances. And also it is the most important thing is that these final phases of the AGB are the ones more important for the dust production, that where we expect more dust to be formed. So in terms of dust budget, this could be studied in many galaxies. This is what we are currently doing with Francesca Annibali, and we will try to, we proposed several exploration. One has been accepted, led by Marta Boyer, and is on Sexton A. Of course, studying these galaxies in the infrared band with MIRI is deliver much more constraint and information. And to be prepared in the last year, to be prepared of this analysis, we explored which could be the best combination of filters with the JWST to better characterize and distinguish the different kind of stars and determine the dust production from them. This was led during her PhD by Esther Marini, and she started working on spectra that were observed by Spitzer in the LMC, reproducing the spectral energy distribution, comparing them with our models, and convolving them into the filters, she found which can be the best combination. And here is the case, one example I make only of carbon-rich stars. You see here in this combination with the 7.7 micron and then 18 micron bands, the carbon stars evolves towards this branch, and we see that, well, of course, this is a sign of increasing dust production, and also we see that we expect that there is a trend with the age, because these are lower masses, and they are expected to produce and reach lower level of obscuration and produce less dust. What really challenged us in this work were these stars. These were identified already in the past. They were well known in the AGB community. They are the extremely red objects, so-called, because they are really enshrouded by carbon dust. And well, you see, even considering some uncertainties, model dependence on the, for example, the mass loss, prescription use, whatever, we may maybe reach some of the stars in the upper part of the diagram, but we are really far from reach the fainter objects, which are extremely obscured, but we do not explain them with a single star approach. I'm saying single because we hypothesized a solution considering binaries, and thinking that maybe if they were in the past being part of a close binary system, they would have interacted and create a common envelope. And we know from the hydrodynamical simulations that the common envelope phase really triggered the mass loss during this really short phase. And this has been even modeled recently, can lead to the production of a large amount of dust. So we thought, well, let's see if it would be feasible to in terms of stellar parameters that should have been needed to have this condition of a closed binary during the AGB carbon star phase. And well, here we have the example of the evolution of the periods of stars of 3, 2.5, and 1.1 solar masses. This is the evolution during the AGB phase. We recognize it. We are showing it in terms of their mass. Since they are losing mass, the time is passing towards this direction, and we consider which would be the possible initial periods that can allow an interaction during the carbon star stage. And we found that actually this is not a small range of years. We have between 2.5 and 15 years range where this could occur. And to see how much dust can be produced during this eventual interaction, we simulate roughly simulate the common envelope phase. I mean, only considering some stages during the AGB evolution and applying a higher mass loss rate, that is one indicated from the hydrodynamical simulation, and let's see how much dust we would form. And the result was pretty encouraging, because you see, even the lowest masses, this is the 1.1 solar mass, can reach really high obscuration and produce a large amount of dust. Of course, this was a really simple approach, really schematized, but just to put the light on the fact that really binary interaction can lead to important dust production. And in particular, what is important is that can increase the dust production for ranges of masses where we would not expect from single stellar evolution. Okay. But, these final phases are quite complicated. The mass loss is really a matter of debate during this phase. We tried really recently to have another point of view to understand better what happens in these last phases of the AGB, looking at the post-AGB phase. So after the tip of the AGB, we have that the stars has lost almost entirely their envelope, start contracting, and moves at constant luminosity towards the PNE phase, and then cool down in the white dwarf cooling sequence. And this is a quite rapid phase, but is really unique. Why? Because between these, after the tip of the last thermal pulse, the tip of the AGB, we do not expect any variation in terms of the surface chemical abundances, and nothing else will occur from this point of view. And the star evolves a lot, constant luminosity, so can give a proxy of the initial mass of the stars. And furthermore, during this warming up of the central star, then in the meantime, the dusty layer are moving away. These are residual dusty layer, but they are expanding. And this is really important, because then in this case, we can really see both the central object and the dusty layer, the residual dusty layer. This is a typical spectral energy distribution of a post-AGB stars. You see the stars is now hotter, between 5 up to even 20,000 Kelvin when then they enter in the PNE phase. And, and the infrared excess shown here refers to the dust layer, that is the residual one that has been formed just at the end of the AGB phase, or probably a little bit after. And this dust is cooler, so this respect to the ones that is formed during the AGB, because it's is expanding. So let the star to appear, and this is really important because we can measure much better in the post-AGB phase all the abundances. You know, in cool stars you have molecular bands, and you really you know better than me that it's absolutely not simple to determine all the abundances, while here the stars are hotter, and the dust does not dominate the emission, and so we can determine better the chemical composition. So why this is important? Because what we are doing now is to take the sample of a post-AGB stars available. There are stars observed in the Magellanic Clouds, but also in the galaxy. And now with the Gaia data, we can estimate the distances better. And so what we do is to fit the spectral energy distribution, and from them we can retrieve the luminosity of the stars, the optical depth from the infrared excess, and the temperature of the dust that is still present around the stars. Then we can compare these luminosities with our evolutionary tracks that has been recently extended from the AGB towards the latest phases. And you see, this is an example of galactic post-AGB stars. Within the error bars, you can try to reconstruct the progenitor mass. This is the main topic of Silvia's PhD, and she already analyzed the post-AGB in the Magellanic Clouds, and now we just finished the analysis of the galaxy. Of course, there are few objects, because this is really a fast phase, but anyway, they can give important proxy, not only for the things that I've said, but also for the latest phases in terms of size scales and mass loss prescription, that mass loss process. Here you have the results of the O-rich post-AGB stars and carbon-rich post-AGB stars in the galaxy, expressed in terms of their luminosity and their optical depth. You know, I know that there are some stars that are spared here and there, but there are some explanation for them, and but believe me that there is a trend that we can see in terms of their luminosity, that is a proxy of their initial mass, and the optical depth of the dust in their circumstellar envelope. And this is also seen in the carbon-rich post-AGB stars. Don't be don't look at the scale of the optical depth at 10 micron, because since here we have the silicate feature, it is higher, but actually carbon is always much more opaque than silicate. So seems less extended, but well, there is dust around the stars. What is peculiar here is that we have a double sequence that depends on the metallicity. This is due to the fact that lower is the metallicity, lower is the oxygen abundance. So the excess in carbon is higher, and this reflects in higher optical depth for these stars. Well, the exploration that is quite new, let's say, that we can do from this analysis is that since we know the temperature of the dust and the optical depth, we can also estimate how far from the star it is. Okay, so if here we have still the carbon star, and making this case, we look now at the distances from the star of the dusty layer. In terms of their optical depth. You see here that we have a trend again, and this is interesting because we see that higher is the mass and lower is the distance from the star of the dusty layer. This is peculiar. Why? Because we would expect, okay, well, this dust is more, and also receive much more push from the radiation pressure, could go farther away. But actually, since these stars evolve really fast and faster from their lower mass counterparts, actually the dust stay closer to the star, so has less time to expand. And making this kind of analysis, we can try to reconstruct the timescales of this expansion, and so try to use this as a proxy of the mass loss process of this phase between the tip of the AGB and the evolution towards the planetary nebula. Okay, well, I hope that I convinced you that there are several applications for the study of dust produced by AGB stars. And this is a summary. And as I was saying, well, we started with the AGB, now the post-AGB phase, but is ongoing the study towards the last stage of the transition, so the planetary nebula phase. And really we hope that this kind of studies can help in estimating the timescales of this transition, which is really important also for stellar population studies. So thank you very much for your attention, and well.
Thank you, Flavia, for the beautiful talk. We have time for questions, so please, Flavia.
I have a question and a comment. In your dust models, obviously, I presume you make some assumption for the dust grain size and density. How much, how well constrained can be this parameter nowadays, and eventually how much the models depend on this assumption?
Well, what we assume is the number of seeds present on which we can form dust. They can be titanium oxide or whatever. So, and this density, is determined from the interstellar
then of individual grain, the density of the grain.
Then we let the grain growth. So we reach the size that we can. I mean, in terms of the key element available, the thermodynamic condition of the wind. So changing the density, it can change for the initial density of the seed on which you form dust. You can form more, larger grains or smaller grains, but then in average, the total amount of dust in a certain way counterbalance, because if you have larger grains, then you can reach the expansion easily and then truncate the dust production. So there is a dependence on this assumption, but is really in a way counterbalanced by the dynamics of the wind.
And the comment is about the possibility to get chemical information from AGB stars. This is, I would say, the most tricky point for this is not really to find regions in the spectrum which are free from severe molecular blending or blanketing, at high spectral resolution, you can, but the tricky point is the determination of the stellar parameters for the chemical analysis, and also the fact that local thermal equilibrium can fail. So, but in this respect, sooner or later, I hope to be able to provide you some information on the AGB.
Wonderful.
To do this kind of study and see. The tricky part is really stellar parameter, because determining temperature and gravity of the star at the moment of the observation is extremely tough.
Yes, let me add also that the point is also that during the AGB phase, you can have a degeneracy between, I mean, if you measure a certain amount, let's say, of nitrogen, carbon, whatever, in some cases you have a degeneracy between, for example, the early AGB phase and the end of the AGB phase, while in the post-AGB phase, you are looking at a picture that is I mean, it's not changing no more, so you can better estimate directly the progenitor mass that you are looking at and which nucleosynthesis has been experienced by this object.
For example, on the AGB phase, the YFJ spectra, you have to produce to get measurements, so that's the math process.
Yeah, you should.
Together we'll see what it's definitely worth to investigate that, but it's tricky because of
Manuel, so Flavia, very nice talk, and I have two questions, if I may. The first one is about the binary common envelope phase. So do you assume that these binaries are primordial binaries that then go to the common envelope phase during the AGB, or they just form during the AGB phase, for example, for encounters between single stars?
We cannot make any assumption on this. We just consider whether if we consider a certain binary system at a certain distance, when the expansion of the radii of the AGB can reach the filling of the Roche lobe, so entering, set up the common envelope phase.
So if
any other
questions on the other way, so given the parameters that you are assuming for the binaries during the AGB phase, would they be able to survive the previous evolutionary phases as a binaries?
Yes, they arrived, yes, so that they can survive from previous, yes, interactions.
And the second question is about the post-AGB, so galactic post-AGB stars. So of course, it's a pretty fast phase, and so the sample is not large. So have you considered also to include post-AGB candidates, at least from local cluster, that can give you easy constraint on the distances?
Well, actually I'm not at right now, so thanks for this point, but
unless you have problems with the mass range.
I'm not sure if they are really post-AGB, as I'm thinking loudly, that they probably would be post-RGB. I don't know. Well,
so I think that there are both,
okay,
or at least there is not a negligible number of post-AGB candidates in lower clusters as well.
Okay, that's very interesting. Okay. Now, what we have done also is to consider only the single post-AGB stars, because of course we have a lot of much more candidates as post-AGBs, but then we relied only on the ones that are single, because they were monitored for a long time by our collaborators, and also they are the shell. The ones that more spherically symmetric shell around them, so both of the things can be simulated by our models. Otherwise, we cannot. Well, we would like to extend also to binaries, post-AGB binaries, but we have not started yet.
Okay.
I have a question concerning the post AGB+ST that you showed for the LNC, the spectrum. So where are the data? Where do the data come from which you constructed the spectrum?
Well, they are all the data available for these stars. So they were collected and analyzed by Devika Kamath from Australia, Macquarie University, and well, they were
So Spitzer data basically
for the infrared Spitzer, but yes, for the LMC case we had the Spitzer, while in the galactic case we also had the WISE and IRAC when available.
And connected to the question. So do you think that with the, for instance, with the JWST resolution, would it be possible to distinguish especially the central star with the envelope?
The central star, I mean, yes, because if we consider NIRCam too, I mean, we cannot see the emission of the central stars, but maybe we can see the valley between the two emissions. We can map that one because yes, the slope that determined mainly determine the luminosity in the fitting process is in the region of the near infrared.
Meaning on the spatial images, you can spatially distinguish an expanding shell.
Well,
the closest galactic HB, but they are have to be very close. And with JWST, we'll not be able to do that in the. You can go a bit further, but I don't think we can make some computations, but I don't think, for example, we can real spatially resolve everything, even in the but we can see.
Yes, please.
I have a curiosity about the one detail, which is the terminal velocity of the AGB wind. So is it a parameter of the model? Because in models where AGB stars are subgrid, in general, a constant value for the wind velocity is assumed. So we're wondering, does it vary as a function of mass?
Yes, as a function of mass and also as a function of the evolutionary stage of along the AGB phase. Because when you have the largest amount of dust produced, you can push the wind more rapidly, and so you can reach up to 30, even 50 kilometers per second. While when you have a lower dust production, in some cases, barely you accelerate the wind. So it's not an input parameter; it's an output for our computation.
And is a function of mass, of stellar mass.
Well, it's not only a matter of stellar mass, because it's also a matter, and this has been studied really deeply from the hydrodynamical simulation that cannot be immediately coupled with the stellar evolution code because they require really huge computational time. But it's a matter of the dust type that you have. So in a way, yes, because the range of masses that produce carbon dust are expected to expand the wind faster respect to the silicates because of this fact that they hardly driven the wind much harder than the carbon dust.
Okay, I might have a quick, maybe last question, which is related to what Emanuele said. So I was struck by these extremely red objects. Do you think is there any hope of detecting a possibly surviving feature of their binarity, or this is beyond?
Well, the post-common envelope phase can be seen better in the PNE, while here we really struggle to find a way to constrain, but since this should be like immediately after the common envelope when dust has been produced and not really expanded, and so it's really enshrouding the system. it's far. It's really hard to find an observational hint of the real presence of. But we are open to suggestions, of course, to improve this idea.
Okay, thank you. So if there are no other questions, not even from home, which seems to be the case, we thank Flavia again.
Thank you.